Here's part 2 of video 7.6 algebra. Part A, it says determine whether the function, rule, or table is linear or exponential. Well, let's review. Having a common difference between the y values means that this is linear. Remember, we were adding $5 every day. Common ratio tells you that you're multiplying, so this would be like if it was doubling or tripling. So this is where we're exponential. So this would be where we multiply. And then I'm going to write add over here. So number 1, here's my x value, and I want to double check what is my y value increasing by each time, or am I multiplying? So between 3 and 5 I'm adding 2, 1 and 3 I'm adding 2, -1 and 1 I'm adding 2. So because I'm adding the same value every time, I would say that this is going to be linear. Because I have a common difference. Number 2, well, this is an equation, and this looks like y equals ab to the x. So I'm going to say this is exponential. And let's take it a step further. Is this growth or decay? So I'm going to look at my b value. If it's greater than 1, it's growth. If it's less than 1, it's decay. So this is going to grow. Here's another word problem. Suppose 30 flower beetles are left undisturbed in a warehouse bin. A beetle population doubles each week. The function f of x equals 30 times 2 to the x gives the population after x weeks. How many beetles will there be after 56 days? So in our function, we start out with 30 beetles, and the population doubles every week. And I see a problem. This is 56 days, so we should figure out how many weeks that is. So I'm going to do 56 days divided by 7 to convert that into weeks, and that is 8 weeks. So 8 is what we're going to plug in for our value of x. So we need our calculators. 30 times 2 to the power of 8. 7,680 beetles. Number 2, why is this function, and this goes along with number 1, why is this what we do, 30 times 2, and why didn't we do 2 times 30 to the power of x? 30 is the initial population. So that's got to be our a value. And the 2 is our growth rate. So that is our b value. So we didn't want to do 30 times a week. We wanted to double every week. And then just to summarize, y equals a times b to the x is the general form for exponential functions. A is always the starting value. And b is the growth or decay rate. And that just depends on the value of b. Okay, why don't you read through this problem and try it. Please pause the video while the students work. So our formula is we start out with 20 rabbits and we triple every half year. So in 3 years, how many half years is that? So we'd take 3 times 2 to get 6. So on our calculators, we're doing 20 times 3 to the power of 6. And our order of operations should do 3 to the 6 first and then times 20. So we get 14,580 rabbits. Here's another exponential function. What is the graph of y equals 0.5 times 3 to the x? So let's make a table of values. And let's make sure some of our values are negative. So we're going to plug in -2, -1, 0, 1, 2, and 3. So if we want to do this by hand, what we can do is 0.5 times times 3 to the power of -2. And we throw that on a calculator. And our coordinate is -2.056. So we get 0.056. So if I graph that, -2, it's just really, really, really close to that line. If I plug in -1, throw it on my calculator, I get 0.167. So then my coordinate is -1, 0.167. So that's just a little bit higher than the last value, and I'm just estimating. So if you want to do this on your graphing calculator, you would type your y equals, and then go ahead and type in your equation, and then we want to look at our table. So what I'm going to do is hit second table, and then that's my values here. So I'm going to scroll down so it starts where our table was. And I'm just going to do a quick screenshot. So again, what we did was we hit our y equals menu, we typed in our equation, and then we're just interested in this table. So under the graph button, we're going to hit second graph, and then that brings up our table. So then I just did a screenshot. So here's what my table looks like. So I'm just going to cover up my mess here. And you can just plug in your values or write them down. And I'm going to finish my graph. So at 0, I get 0.5. At 1, I get 1.5. At 2, I get 4.5. So notice how it starts getting bigger faster. And then that's where our graph, 13.5 is off my graph. So then I'm going to connect my dots, and you should kind of know what this is going to look like. It's going to be one of those hockey sticks, so it should not cross the x-axis. It's not going to get smaller than 0. Our population can't be negative, so that's why it's going to just stay kind of parallel to that line almost. So our domain are the numbers that we can plug in, and we can plug in any number that we want. And the range is going to be any number that's on top of this x-axis. So it's going to be all positive values. So I'm going to say positive real numbers because it's not going to be any negatives. So why don't you try these problems? It says evaluate each function for the given value. So I'll do the first one with you. So this is like 1 times 4 to the power of 3, but that 1 just isn't there. So this is going to be growth, so we're going to get bigger than 1. So really we're just doing 4 to the third, which is 64. So why don't you try these 3. Please pause the video while the students work. And here are the rest of the answers. 486, 103.09, and 5. Numbers 1, 2, and 3, are these exponential growth or decay? So number 1 is decay. Number 2 is growth. Number 3 is decay. So in review, if it is growth, our value has to be greater than 1. If it's decay, our B value has to be between 0 and 1. This concludes my lesson.